Now we come towards the laws of radioactive disintegration, which I have already enunciated. And now we come to the main concept. If n is equal to n naught of the active nuclei at time t, n minus dn, that is small number of atoms, dn means small number of atoms, will be equal to number of active nuclei after time interval of dt. Therefore, rate of decay is minus of dn over dt. According to Rutherford and Soddy law of radioactivity, at any instant the rate of decay of a radioactive atom is proportional to the number of atoms present at that instant. Rate of decay is proportional to n. I have already explained that radioactivity is determined by the rate of disintegration and dn by dt is proportional to n. So we have written minus dn by dt is equal to proportional to n. That is, as the disintegration goes on increasing, the number of atoms goes on decreasing. So dn over dt is equal to lambda n, or if we don't write minus sign towards the left, we can write it towards the right side, and lambda is called the decay constant. If ni and n naught of the active nuclei at time t1, nf, number of active nuclei left at time tf, then we integrate the function, that is 1 over n dn, from the limits, initial number of atoms to the final number of atoms, initial time to final time. I have already explained it in terms of t is equal to naught, and finally our expression will come minus lambda into tf minus ti. So the final function will become minus lambda into tf minus ti. That is the final time minus the initial time, and lambda is a constant. The ratio of final number of atoms to the initial number of atoms, that is given by function e to the power minus lambda into tf minus ti, that is final time and the initial time. And if tf is equal to t and ti is equal to 0, and f is equal to n and ni is equal to n naught, then n over n naught is equal to e to the power minus lambda t. And from this we get n is equal to n naught e to the power minus lambda t, equation number 1. This is called general equation of radioactivity. Now equation 1 is known as Rutherford and Soddy's exponential equation of radioactivity. If t is infinity, then n is 0. Therefore, for a complete decay of the radioactive nuclei, it takes infinite time. Half-life, I have already explained. That is, half-life of radioactive element is the time interval in which half of the radioactive sample disintegrate. Now we come toward the physical significance of the half-life. If half-life of a radioactive nuclei is more than in given time interval, probability of its availability is also more. Half-life of an element does not depend on physical and chemical circumstances. So n by n naught is equal to 1 over 2 to the power small t over capital T. Graph between the number of active nuclei left and time of decay, that is indicated in the figure. So what we are finding that on the x-axis we have taken time t, and on the y-axis we have taken the number of atoms n. So original number of atoms will be n naught at t is equal to 0. Now as the time starts increasing on the x-axis, the number of atoms will go on decreasing, as shown in the exponential graph. That is, t increasing, the number of atoms decreasing. So if we consider the half-life, that is small t is capital T, then in the first half-life, n naught will drop to n naught over 2. In the second half-life, it will become n naught over 4. In the third half-life, it will become n naught over 8, and so on. So, for the exponential equation, the number of atoms decrease in geometric sequence. The average life or the mean life, which is represented by tau, the time for which a radioactive material remains active, is defined as the mean life of that material. Tau is given by sum of the lives of all the nuclei divided by the total number of nuclei present And in order to represent it, better is to integrate a function, that is integration of t with respect to n divided by n naught. The limits of integration will be from 0 to infinity. So we can say that we are integrating t with respect to n. So these are the two different variables. So t is taken out of the integration sign and we integrate 1 with respect to n, and that will be n, and the limits will be put as 0 to infinity, that is infinity minus 0 divided by n naught. So the average time taken in decaying by the nuclei of an element is defined as its mean life t, and t tau is equal to 1 over lambda. N over n naught is minus lambda t. Negative sign is always indicating decrease in the number of atoms. The magnitude of the inverse of the slope of n over n naught and t curve is known as mean life. If n is equal to n naught e to the power minus lambda t, and if t is equal to 1 over lambda, then n is equal to n naught e to the power minus 1, and that will become n naught over e is equal to n over 2.718. And by simplifying, the number comes to 0.37 of n naught. Therefore, if tau is t, then 1 over lambda, that is tau is equal to t is equal to 1 over lambda, then n is equal to n naught over e, and e can be replaced by 2.303. So that's why the number comes as 0.37 of n naught. N naught means the original number of radioactive atoms at t is equal to 0, and n is the number of atoms in time t. The mean life of a radioactive nuclei is equal to that time in which the number of nuclei left becomes either 1 over e times the original nuclei, or approximately 37% of the original nuclei. The number of decayed nuclei in the mean life, that is given by n naught minus n, where n naught is the original number of radioactive nuclei and as the number of radioactive atoms when decay started. So we can write this equation as n naught minus n naught over e, because n is calculated to be n naught over e. So out of this, we will take out some common number, that is n naught into 1 minus 1 over e. So the net number will become e minus 1 over e. So it will become 0.63 of n naught. We have to compute the value of e, that is 2.303. Now we come towards mean life, that is the mean life is equal to, or the average life is equal to that time in which number of decayed nuclei becomes either e minus 1 over e times the original nuclei, or approximately 63% of the original nuclei. This we have calculated in the earlier program. Fraction of the atom nuclei left will be n over n naught. Fraction of the decay nuclei 1 minus n over n naught, and that is found to be n naught minus n over n naught, where n naught is greater than n. Now we come towards the half-life, the mean life, and the decay constant for a particular nuclei always remain constant. If the material will change, then only these numbers will change, not otherwise. Now we come towards the decay constant, lambda. It is expressed in per second, per minute, per hour, per day. So lambda is dn by dt over n. So it is just ratio, that is the rate of decay at a given instant divided by the number of active nuclei at that instant t. So lambda can be given by negative of rate of disintegration divided by dt, that is equal to probability of the decay in unit. So lambda is t to the power minus 1 or 1 over t, then n is equal to n naught over e, and this value is found to be 0.37 times of n naught. Decay constant is equal to inverse of that time in which number of active nuclei left becomes either 1 over e times or approximately 37% of the original nuclei. Now, general equation of radioactivity, as we have discussed earlier, that is n is equal to n naught e to the power minus lambda t. Now, if n is comparable to the mass m, that is, if n atoms are existing in time t, and those n atoms constitute mass m. Similarly, n naught is the number of atoms in time t0, and equivalent amount of mass is m naught. Then we can write this equation as m is equal to m naught e to the power minus lambda t. So instead of n is equal to n naught power minus lambda t, we can write the number as m is equal to m naught e to the power minus lambda t. M naught is the mass of the radioactive nuclei at time t0, and m is equal to mass of the radioactive nuclei at time t. Decay constant is equal to the inverse of the time in which 63% of the initial atoms being decayed. Units of decay constant will be, that is, per second, per minute, or per year, that is second to the power minus 1, minute to the power minus 1, or year to the power minus 1.